He's a professor of energy policy and economics. I've known Seth for several years. This is the first time we've managed to get him to come to Cornell and talk. Seth has a really interesting and diverse background in engineering, economics, as well as more recently in regulatory policy, okay, and governance, which is a great skill set to have as we address these important questions of how we're going to really transition our grid in the future. The last few years, and I should also add that in addition to his professional accolades, he's also a hop farmer, which is, he likes his beer, but I'm going to ask you to save your beer questions until the end of the seminar. And during the seminar, we're going to stick with the sort of the more engineering and economics of the power grid type topic. So I'm really excited to have him here. He's a perfect speaker for the energy seminar, and I'm not going to take up any more of his clock time talking. So with that, I'm going to thank Seth for being here, and he's going to talk to us today about managing the gassy power grid, which is something he's been working on for the last several years, looking at how to coordinate or how to manage coordinated gas grids with power grids as those things become more tightly coupled in recent years. So thank you, Seth, and with that, I will have you take it away.
Okay,
all right?
Thank you. Such preemptive applause. All right.
Well, that was for me, Seth.
That was as well it should be. Okay, so I want to thank Lindsay for inviting me up here. I want to thank everybody for, did you come through these sort of weird maze of underground tunnels that I have been led through today, or did you walk outside in like the terrible weather? But I want to thank everybody for coming. Okay, so here are the rules. I don't actually care if I get through everything I have to say. So if people have questions as I'm talking, just like feel free to interrupt me, okay? Particularly if you are a student and you have questions. So and I think there's also time after this to talk about this stuff. I get to come to Cornell and be treated like royalty, but most of the actual work was done by my collaborators at the Los Alamos lab, at Georgia Tech, and by some students at Penn State who should be on this slide but aren't because I'm a terrible person. All right. Okay. So I think especially since I see so many students and people younger than me in the audience, this is a parable that is masquerading as a research talk. Okay, and so I'll give you since people have to leave early, I'll give you the moral first. Okay, so the moral of the story is go talk to real people. If you are really interested in this stuff, right, you can certainly talk to your professors. They're very nice, right? They don't bite. But talk to real people whenever you can. And and don't ignore their flip comments, because those are often the most revealing things, right? So the story of this, the reason that this is the moral of the story, okay, is that how I wound up here today, right? Kind of the genesis of this, which is basically some work that was funded by NSF that has been going on for the past several years. So the genesis of this was this kind of geeky power grid conference that I go to a lot. Lindsay goes to it a lot. And a number of years ago, we had basically a panel discussion, right, where we had the CEOs of some of the companies that run the regional power grids in this part of the country. So in New York, and the area where I live down here is run by an entity called PJM. So we had these CEOs come in, and they, it was cool. They said their thing. And so when it got to the point where we got to ask them questions, okay, we asked them the one question that, as students or researchers, that you should always ask when you're in the same room as captains of industry. And that question is, what keeps you up at night? Okay, so, we asked them the what keeps you up at night question, okay? And to a man, because they were all men, to a man, they said natural gas. Okay, these are people that run the power grid. Okay, and they said that, and I had been like the answer that I was expecting, okay, was I'm worried about how I'm going to manage all this wind power that's coming onto my system, or I'm worried about like cybersecurity, people trying to hack into the power grid and causing blackouts and stuff. Okay, I was not expecting them to say natural gas. Okay, because the idiot that I am, my model was that and I mean this was about the time that like that the activity in drilling for unconventional natural gas in Pennsylvania and other places was really ramping up. Okay, and so stupid me, I thought this was a great thing, right? Because it meant one of the primary drivers of electricity costs, okay, is the price of natural gas. Right? All this drilling activity had happened. The price of natural gas had fallen into the toilet. I thought this was great, right? And so it was a real surprise to basically hear people say that they were worried about natural gas. So after the panel was over, I was talking to one of them, the person who used to be the CEO of the PJM regional grid operator, right? And so we were sort of talking about this issue, and he said that the reason that he was worried about it was because he was really concerned about how dependent the power grid that his company managed was going to become on a single fuel. Okay, and he said that like trying to deal with like the pipeline operators was a total headache, right? And he said he was just really worried about it. Okay, and so I asked him what do you do about this, right? And he said, here's my idea. Okay, he said here's my idea. What I'm going to do is I'm going to rig the rule. He didn't say rig. He said I'm going to rig the rules of the electricity market to encourage all these companies that build power plants and are starting to build lots of gas-fired power plants to build them in the same area, okay, where people are drilling for gas, okay, to basically have like wellhead natural gas plants, okay? So you'll just take the gas out of the ground, move it directly to the power plant, and then I can deal with building the wires that will take the electricity to other places, okay? And I said, is that a good idea? Because I didn't know what else to say. And he said, I don't know. And so that was kind of like the flip comment that sort of stuck with me. Okay, that this was somebody whose company runs the biggest electricity market on Earth, right? And he had this idea that in the end never went anywhere because he retired. But he sort of had this idea to solve this problem that he saw coming down the pike, and he didn't really have any way to think about whether it was a good idea or not. So I started thinking about this, and what I basically found was that there were not any good kind of off-the-shelf tools or models or anything, right, for us to think through this problem of sort of how do we manage the increasing dependence of one of these networks on another one of these networks, okay? And so I thought that was sort of interesting. And then so that kind of turned into a sabbatical project, right? And so I spent some time in New Mexico and up at Los Alamos with the Los Alamos folks working on sort of trying to build these models, right? And we made enough headway that NSF gave us a grant for it. Now we have stuff, and I get to come here and talk about it. So that is the moral of my story. So, okay. So this is basically a picture of the kind of problem that these regional power grid operators we're talking about. Okay, so this area in blue is called the PJM system, and the area in blue is basically the footprint of the national power grid that is managed by this company PJM. Okay, so everywhere that you see a blue dot, okay, those are, and this picture is a couple years old, but it's still a good one. So everywhere you see a blue dot, that is a power plant that is shut down. Okay, so these are mostly coal plants. Okay, and they are mostly located kind of in the western half of the PJM territory. Okay, the red dots are power plants that at the time this picture was made had told PJM, the grid operator, that they were going to shut down. Okay, and then the green dots are new natural gas power plants. Okay, now so so this picture, right, made these CEOs nervous for two reasons. Okay, one is that kind of what you see in this picture is just like a technology transition, right? PJM was using lots of coal, right? It has started to use lots of natural gas, right? And this is basically continued. Okay, the other reason that this makes, or that this made these CEOs nervous, okay, is that the basically kind of the geography of electricity production in this kind of wide area is really changing, right? Basically, the power grid for this part of the country was basically engineered to take lots and lots of coal power from the Ohio River Valley and move it over long distances to places like Washington, D.C. Okay, and so what's happening, okay, is that kind of like the geography of power production is moving east. Okay, right, and you can see that it's getting very clustered. You see where all these green dots are. Okay, in one sense, this is not such a bad thing, right? Because because there's a lot of electricity production that is moving closer to the main areas of consumption. Okay, so you have to move it less far with big transmission lines. Okay, in a sense, maybe that is easier. Okay, but if you sort of look at where these green dots are clustered, okay, why are they here, right? All the natural gas comes from basically, or all the new natural gas is coming from Pennsylvania and West Virginia. Okay, so why are the gas plants locating here? Right. The reason that they're locating there is because this is basically this area, okay, is the location of kind of one of the major gas pipelines that moves natural gas from the Gulf Coast to the Northeast. Right. It's called the Transco system. All right. And so one of the reasons that this is sort of making people nervous, right, is that because of the location decisions that are being made by these gas plants, right, you have this big regional power grid that is becoming more and more dependent basically on a single pipeline corridor. Okay, so I mean, I think this picture says a lot. Okay, but it basically explains why all these CEOs are nervous about what is effectively a plentiful supply of cheap fuel. Mm-hmm.
Is there any built-in redundancy today in that main line? And one, and two, is there any regulatory plan for either additional storage or some redundancy and backup in the future?
The answer to the first question is along an individual pipeline. So like these pipeline corridors are typically not single pipes. Okay, they are typically kind of multiple pipes in parallel. Okay, and some gas generators, not all, but some of the gas generators will effectively have interconnections to more than one of these parallel pipes, so that if one of them fails, then they can still draw gas from the other ones. Okay, this does not provide resiliency against a situation I'll talk about in a second, okay, where you have a combination of like extreme cold weather and coincident high demand for electricity and natural gas, okay, where you have these parallel pipes, but they effectively all get derated at the same time, right? Because when it gets really cold, then basically there are pressure deratings on the natural gas system. Okay, so it doesn't deal with that kind of it can deal with like the failure of a single parallel component. Okay, your second question is a really good one. If I give you the full answer, then I might as well just stop talking. But you can hang on to it, okay? Because the short answer is there's a lot of there's a lot of pipelines in the pipeline. Can I say that? There's a lot of investment that is planned to move natural gas around from these new producing areas. If you're worried about power grid resiliency, this new investment is probably not in the right place. Okay. Okay. So I should this is a great picture. I could talk about this picture for like an hour. But this basically explains kind of why these CEOs are nervous about the increasing dependence of the grid on natural gas. Okay. In case anybody is curious about this, the natural gas transportation system is becoming increasingly dependent on the grid. Okay. So when I started doing research on this about 5 or 6 years ago, there were sorry, let me back up a second. How do you move natural gas around? Okay, you need to move natural gas around by maintaining pressure in the pipeline system. Okay, so natural gas comes out of a well at very high pressure. Okay, but then if you want to move it long distances, you have to maintain that pressure in the pipeline system. And the way that you do that is through compressors. Right, so there are these giant compressors that are located at various points on pipeline systems. So for example, if you follow the dots right here, you can see every compressor on this Transco line. Okay, so historically, these compressor stations used basically reciprocating engines that ran on natural gas, and the compressor station would essentially skim a little bit of the gas that would come through, okay, to run the engine, okay. An alternative, right, is that you could have an electric engine, right, and basically connect the compressor station to the grid, okay. That used to almost never happen, okay. But in some areas of the country, notably here, since this is sort of where we are and I'm going to talk about it, okay, it is becoming much more common for compressor stations on on basically larger compressor stations that are built to handle higher flows at higher pressures for new pipelines, all this kind of stuff. These are increasingly more likely to use electricity rather than skimming natural gas off the top, basically so that they can get environmental permits. Okay, in some places there are some concerns about like safety and security and things like that, but I think especially in this region, those decisions are really being driven by the environmental components of the permitting process. Okay, so you have these two systems where the grid is clearly increasingly dependent on the gas transmission system, but the gas transmission system in some areas is also becoming more dependent on the power grid. Okay, so this basically doesn't just go one way. Okay, yeah.
Quick question: what's the power rating for those it's a large compression station. Like how many megawatts? Or
that off the top of my head, I don't know. But it's like tens, not hundreds. Okay. So not that long after we had these, basically had these CEOs giving this panel at this sort of geeky conference, there was this event that happened in the Northeast, okay, which is sort of historically we have to give everything a cute name, and this one was called the Polar Vortex, okay, and it was a period of extreme cold that happened in January 2014, right, and what this period of extreme cold produced was a coincident demand for electricity and natural gas for heating that basically never happens, right? So, the people who sort of plan and operate the power grid, right? They, in their world, right, demand is high in the summer and not quite as high in the winter, okay? During this polar vortex event, you basically had that flipped, okay? So these power grids that normally experience peak demand in the summer saw their annual peak demand in the winter, okay? Which again, almost never happens, right? And so the power grid in my area was basically driven to the point of failure because you had increased competition for limited natural gas supply, right, or for finite natural gas supply. You had pressure restrictions on the pipeline system, which essentially reduced the flow rate of natural gas, okay? And then you had basically power plants that did not have essentially guaranteed delivery rights for natural gas, okay? And so they got curtailed, okay, by the gas transmission operators so that they could deliver more gas to homes and businesses. Okay, so that's and so this was sort of, I mean, this was one of these kind of watershed events that.
Mexico or?
No, so this is in Pennsylvania.
I see.
Okay, so the year that so there was also a situation, okay, in New Mexico, okay. A couple years earlier, where you had a failure on the power grid that cascaded into a failure on the gas delivery system, okay? And there were a whole bunch of people in northern New Mexico who lost gas service in the middle of winter, right? Which northern New Mexico actually gets cold in the middle of winter, okay? So this was a fairly serious thing, okay? So what do so I mean, going back to this conversation that I had with the former CEO of PJM, right? How do you think about ways in which you might sort of respond to situations like this, right? And knowing that the power grid is becoming increasingly dependent on natural gas, what do you do about it? Okay? And how do you think about what to do about it? All right? So one of the and kind of the what do you do about it, you can basically separate into two kinds of options, okay? One is you can basically try to change the way that we operate these systems on kind of a day-to-day basis, okay? And this was part of the problem during the polar vortex, okay? Which was that the entities that operated the power grid, okay, basically did so without a whole ton of situational awareness about what was going on the natural gas system, okay? So the folks who ran the power grid essentially committed a whole bunch of gas-fired power plants to run to meet high electricity demand, okay? When it comes to actual real-time operations, right, these plants actually couldn't run because they didn't have fuel, okay? And so the reason that the power grid operator basically made this decision that in hindsight seems foolish, okay, was because they did not really understand just how constrained the natural gas system was going to be, right, at the time that they made these decisions to commit gas-fired power plants to run, right? And so there's this whole, basically there's a process by which the natural gas market clears, okay, where supply and demand are matched and that produces a price, okay? And that process happens very asynchronously with how the electricity market operates, okay? So basically, FERC responded to the Polar Vortex essentially by ordering the companies that run the natural gas transmission system, okay, to develop what I'll call a very near real-time market for natural gas, okay? And they have done this, okay, but this does not seem to have sort of solved the coordination problem, in part because this near real-time natural gas market, basically nobody goes into it unless something bad happens and they need to go like panic buy. Okay, so it's as a market solution, it doesn't seem to have done kind of what FERC had intended. Okay, but if I have time, I'll come back to kind of the operations part of this. Okay, so when I was talking to the CEO of PJM, he was not thinking about operations because he did not think that he could get the natural gas market to change, right, just because he wanted it to, right? And so he was thinking basically about planning options, right? How basically what could he do on the system that he was on the system that he was operating, okay, in order to kind of ameliorate this dependence on the gas pipeline system, okay? And there are different planning options that you can think about, okay? And it was really kind of these planning options that motivated the development of this kind of modeling framework that I'm going to talk about, okay? So with my colleagues and I started thinking about how we might kind of think about evaluating different kinds of planning options. We have papers and stuff which you can go read. But basically, what we needed to put together, which basically didn't exist, okay? And we put this together. It's in the public domain. It's all on GitHub if anybody wants to go play with it, okay? So what we basically needed was some was basically a modeling framework that could capture the relevant properties of how the power grid works, could capture the relevant properties of steady state gas flow, okay? If any of you are big pipeline modelers or like petroleum engineers or anything like that, some of like the dynamics of gas flow are not really captured here, so I'll admit that out front, right? And then you can tell me later that these are things that we should consider. But but for a planning model, I think this is probably not a big deal, okay? So we need to think about kind of how the power grid works. We need to think about how the gas pipeline system works, right? And we also need to basically capture the interface between these two things, right? So, you have power plants that will draw natural gas from the gas transmission system. This will affect pressures and other things on the gas transmission system. Okay, so we have this kind of coupled system model. Okay, and then we essentially coupled that to a kind of fairly kind of traditional standard least cost planning model. Okay, so you're going to build stuff, right, to meet some level of demand in like a least cost way as possible. Okay, and we also have coupled this to like a steady state operational model of both systems. Okay, and what we were trying to basically get at, right, was that part of what happens in the natural gas market when you have when you have constraints like you had during this polar vortex period is you see these kind of extreme price spikes. Okay, like the price in the natural gas market went from $4 a million BTU to like $120 a million BTU, essentially overnight. Okay, And so one of the things that we basically wanted to capture, okay, in this modeling framework was that any investment decisions that you make in either the power grid or the gas pipeline network are going to have impacts not only on flows, right, sort of operational system variables, but they're also going to affect price formation. Okay, so if you essentially increase the deliverability of natural gas into a certain area, even in conditions of high stress, that additional infrastructure is going to ameliorate some of the price impact. Okay, which is then going to change the economics of how the power grid works, because all of a sudden natural gas looks cheaper. Okay, so basically the kind of framework that we have is essentially coupling a system model to an optimization problem that seeks to minimize basically the capital cost for expansions, okay, plus the operational cost, okay, and the operational cost in turn depends on the expansion decisions that you make. Okay, that's what all this mathy stuff looks like.
So is it completely transparent? So the power grid knows all the information about the natural gas system, and the natural gas system knows all the information about the power grid? Yeah. So the first piece of this that I'm going to talk about, right, is totally transparent. Okay, because this is an optimization framework, and because at the time we were doing this part of it, we didn't really know what we were doing, and it was sort of crazy enough already. There's another implicit assumption in here, which is totally unrealistic, okay, is that there's essentially a single decision maker here, right? So you basically have like a single optimizer for the power grid and the regional gas pipeline system, okay, which is not the way things work at all, right? So regionally, you do have single optimizers for the power grid, right? There's a grid operator that solves a least cost optimization problem to dispatch power plants. This is not the way the natural gas system works at all, right? The control of the natural gas system is very highly decentralized. Okay.
So I don't know whether you may get to this later, but one thing I'm curious about. I know we're not supposed to ask questions.
No, my rule is you are.
No,
Well, we're the old.
No, I said especially students.
So the changing thing so New York now has obviously suppression of shale gas, but there are other forces at work here, namely biogas injection, which could come from farms and add additional supply. I'll bet that's not accounted for at all.
No,
Right.
not in the slightest.
Right. But that would have to be eventually, partly because you need the pipelines and the pumping station capacity to re-inject. So that would be an interesting cost issue.
So in that model, is there embedded somewhere in there joint use storage facilities so it can be drawn upon by either natural gas folks or it can be drawn upon by the electricity folks, state or strategic storage?
There are storage facilities, okay, and when I get to kind of the test system, I'll talk about that in a second.
They're not
okay.
expanding, though, right? You'd use existing ones. Right?
So we use existing ones, right? And I mean we can model storage expansion.
Right.
We have done that a little bit. Okay. Okay. All right. So kind of under the hood, and this is basically, I think this is about all the math I have here. Okay. So basically the kind of the structure of this optimization problem, right, is we have some terms that basically represent expansion costs. Okay. And basically the way that we have the way that we represent kind of the gas market clearing, okay, is that we have basically this kind of price sensitivity curve, right? That where basically the price of natural gas increases as demand increases. Okay, and I'll talk a little about that in the more. Okay, and then we have a kind of a second term, which basically represents the additional compression cost that you will get in order to effectively reroute gas around congested areas. Okay. All right. When I basically talk about kind of the sensitivity of natural gas prices during these kind of extreme events, this is a very location-specific thing. Okay. So this picture right here is basically a picture of natural gas prices for each day during that polar vortex event in basically western Pennsylvania, kind of northern and western Pennsylvania. So this is the big producing area, okay? And basically the relevant thing here is as demand, okay, for natural gas basically goes up by about a factor of 5, okay, the price does not change very much, okay? In contrast, this picture has natural gas prices for the same period for an area of the pipeline system that is called Transco Zone 6 non-New York. So that's your logo for the day. It's basically this area around New York City, okay, kind of, it goes sort of from like northern New Jersey, kind of like, or basically from northern New Jersey, like around New York City like this with a donut hole in the middle for New York City, okay? So that's your lingo for the day. So during this same period, okay, basically the demand for natural gas increased by a much smaller amount, okay, and you had a fairly massive increase in the price. Okay, the axes here are all normalized, right? But you had this very different pricing behavior in different parts of the network. Okay, and this is something that we wanted to be able to capture because it's sort of, it's obviously going to be more. It's there's going to be a greater economic impact if you can deliver more gas or electricity, okay, to a very congested area. Okay. This is so if anybody, if you have worked with these models, you know that they can be kind of nasty, right? So we basically have all these equations that govern electric power flow. There's basically non-convexities that show up all over the place. In natural gas flow, there are basically in steady state natural gas flow. In transient gas flow is a mess. But even in steady state natural gas flow, okay, from a modeling standpoint, it's hard because you have these non-convexities that show up in two places. Okay, one is basically this is the fundamental steady state gas flow equation called the Weymouth equation. Okay, and then there are basically all of this mess of other equations here are basically pressure constraints. Okay, and there are these bilinear terms that show up in the pressure constraints that you have to deal with. Okay, and so basically we have these kind of McCormick and Trigg relaxations that work pretty nicely for these things. And if you want to know more, ask me about those later. Okay. Yes.
Yeah. Looking at the equation, I would quite, I'm still thinking about the polar vortex example again. So, do you have temperature-dependent terms in the equation at all?
Yes, the
demand days or something.
Yeah. No. This is for gas flow, right?
For gas flow,
Yeah.
right.
Degree days.
See how your model can help deal with the future polar vortex-ish condition. Right? So
you have a norm, and then you can impose a transient on top of it for a big.
Yeah. So because this is a steady state model, like we don't really have that. Okay. All right. So we have basically there's a kind of a first order dynamic model. Okay. That we are working on to make this a little more suitable for operations modeling, right? Because you sort of have hit the nail on the head that if all you want to do is solve a planning problem, okay, this is a perfectly reasonable thing to do, okay. If you want to then also look at operational constraints, right, in a sort of in a close way, that's really important. Okay, this kind of this framework is not as well suited for it because it doesn't capture the temperature effects on gas flow, which operationally over scales of hours are important. Okay. So we have this big optimization framework. The other thing that we did not have was basically a computational testbed on which to implement this thing. Those of you who, if you have worked in the power grid space, right, there is this huge archive of like computational test systems, right, little sort of toy power grids that you can plug into computer models, right. There is no such thing on the natural gas side, so we went and built one. And so what we did was we took and I realize now that this is like the color scheme I used here is terrible. So what we did was we took an existing kind of power grid test case, which represents more or less kind of the topology of the northeastern power grid. Those are the things in blue, if you can see that. Okay, and then what we did was basically to go to the websites of the major gas transmission operators, right, who operate basically kind of from Pennsylvania on northeastward. Okay, so from these gas transmission operators, you can get system maps, right? You can get the locations of compressor stations. You can get they have more operational data than you think they do. They just don't archive it very well, and unless you know where to find it or want to spend half your sabbatical looking for it, it's not very transparent. Okay, so we basically built this test system. Okay, and so the red things in the kind of the red piece is the natural gas transmission system. The blue piece is the power transmission system, and if you can see the yellow dots, those are the coupling points. Okay, so like here, like those are points where you have one or more natural gas plants. Okay, and so this was basically the system that we used as kind of the platform to implement this sort of optimization problem. Okay, so we can do all sorts of different experiments with this, and I'm gonna talk about just a couple of them. Okay, just as examples, and so one of the things to remember here that we're doing that's not, again, it's not super realistic, is we have this system that geographically or is sort of representative of a wide geographic area where you have multiple entities that are making decisions, and we're basically treating it like one coherently managed system, which it actually is not. Okay, so I'll beg for forgiveness now. Okay, so just to sort of, just as examples, okay, of the kinds of planning problems that we have thrown at this modeling framework, okay, and kind of how you get sort of different answers, right? So the answer sort of depends on the problem that you throw at the model and the problem that you want to solve. Okay. Okay. So the kind of the first scenario is that we're going to take the demand profile for electricity and gas, okay, and we're going to increase it uniformly everywhere. Okay. So demand just goes up everywhere. Okay. Okay. And basically, the solution to that planning problem, right, is essentially to build is basically to build more pipelines to carry fuel to existing power plants, right, and then you can basically move some gas by wire. Okay, if demand is and if you can see this, basically these lines, so there are these darker lines here. Those are areas where.
Turn these lights. I think it'll work.
Oh, okay.
If you can stand it.
That's fine with me. It's like the movies. So the areas where you have kind of the darker lines here, right? This is basically, these are the expansion solutions for the gas transmission network, right? And also for the power grid, right? Some of them are easier to see than others. This one is fairly easy to see. There's some down here which I think are probably harder to see. Okay. So we also basically modeled a scenario where you have more, but where basically the increase in demand is not uniform over space. Okay, so you have some areas where demand grows faster than others. Okay, and so in that scenario, you're not just going to build more stuff, but you're going to build it in different places. Okay, and so the kind of solution that you get out of this is basically to move as much fuel as possible, okay, to places that are seeing high increase that are basically seeing high increase in demand. So you can basically, so here you can see that there's basically all of this infrastructure that is built to move fuel to New York, okay, and then there's more stuff you build in New York to serve that increased local demand, okay. Now, how easy is it to build something in New York? Right? And this could be anywhere in New York State, right? This is something that we don't really think about, right? I mean, we could incorporate that with some kind of, cost term or something like that. But just to be sort of clear that they're, these are computational experiments, and when you look at stuff like this, right? You have to think about it in some kind of context, right? That, realistically, this involves building a lot of infrastructure that would probably be hard to cite, okay? The one that we thought was actually sort of the most interesting was we sort of looked at kind of like the polar vortex example, okay? So if you have an increase in electricity and natural gas demand, okay, which is uniform over space, but relative to kind of how things normally are, okay, is basically on the order of magnitude of what we saw during this polar vortex episode, okay. If that was basically what you wanted to plan for, okay, and this is a typical planning objective, right? You're going to plan for peak demand, which is like building stuff for Christmas and Easter, right? So what comes out of this is there's two interesting things that come out of this, okay? One is that if you're really worried about these kinds of events, okay, and you want to solve this problem with basically by expanding infrastructure, right? Then it is going to be fairly massively expensive, right? You're basically talking about like an investment plan that is substantially larger than even what a lot of pipeline companies are basically throwing in, okay? And so that's fairly obvious, right? Basically, any planning model is going to tell you that if you throw high enough demand in, okay? The thing that comes out of this, which I think is more interesting, okay, and I think is probably a little more policy relevant, is that the way that this modeling framework is set up is, it's very focused on the gas-electric interface. Okay, and so the expansion plans that come out of these things are really focused on being able to deliver natural gas to power plants. All right, and so the places that you see kind of pipeline expansion coming out of this modeling problem, okay, are sort of the places that you would expect. These are high demand areas. Okay, so you're kind of wind up connecting the producing areas to the high demand areas. Okay. Yep.
would have selected an expansion so large out in northern Maine?
In northern,
That's a 100-mile line.
Yeah. So. So this is a power grid expansion. Okay. I think this is a little bit of an artifact of how we increased electricity demand kind of uniformly across space. Okay. And there's within the within the system model there's basically there's a lot of generation capacity up there, and basically what this is capturing is that in this planning scenario you would move more electricity from Canada kind of down into New England.
Doesn't that coincide with the Quebec and Ontario power extensions, the hydro expansion?
Yeah, and so it's a little bit of an artifact of the model. Okay, but on the other hand, this is kind of what's happening in New England anyway, right? And what is probably going to have to happen in New York if it's actually serious about its carbon reduction goals, right? Is you're going to wind up importing a lot of hydropower from Canada. Okay, so the interesting thing about gas investment that comes out of this, okay, is that as kind of investment alternatives that are available within this modeling framework, we basically took every major pipeline project that is currently planned for the Northeast and threw it into the model as basically pipelines that the least cost planner could choose, right? And the only one that is actually planned, which the model chose, is this one. Okay, and the reason that this is important, okay, is basically goes back to this kind of disconnect between the way that these two infrastructures are run, right? The natural gas transmission system, they don't make investments to make the power grid happy, right? They view their customers as basically industry and natural gas utilities, okay? And whether we get this to change or how we get this to change is, I think is an interesting question, right? But from a planning perspective, there's kind of a fundamental disconnect between kind of what the power grid needs, which is getting a lot of attention, okay, and the way that gas pipeline operators have historically made decisions and continue to make decisions based on their business model, okay, which is essentially selling natural gas to industry and to distribution companies. Was there? I thought I saw a hand. No.
This is 50 minutes. I think it's the end of the hour.
Okay.
After the 50-minute period.
Okay. All right.